So now we'll have Mohamed Al-Husseini, who is an assistant professor at KAUST. And since fall, he has been a senior member of IEEE and a member of the International Summit community. Previously, he was a visiting faculty at Stanford. He's been at Baidu, Facebook, and he has a long trajectory. His primary research interest is in computer vision and especially in efficient multimodal learning with limited data in zero and few shot learning and vision and language.
I don't know why it goes to the second slide. Maybe you have a timer. There's something here. Thank you so much for the nice introduction. I would like to thank the organizers and for organizing this great event, and it feels great to be back in person. So today I would like to discuss with you what we might refer to as imagination supervised machines and how it can be used for some useful task. It can relate to some of the topics that I think this was discussed today in this workshop. Before I start, I'd like to thank a lot of students and interns that has contributed as members of the Vision Care Group that I lead at KAUST. So we are all aware about supervised learning, semi-supervised learning and unsupervised learning, which has led to tremendous success over the past decade. And in supervised learning, we have access to all the labels. So in the standard recognition task, where we want to recognize few classes like cats and dogs, we have access to all the labels. In semi-supervised, we have access to some labels. In unsupervised learning, we have a large set of unlabeled data, and we need to learn representation, but we don't have access to any labels. One thing I would like to suggest today is that we can also improve learning systems by imaginary data. And this can happen through different applications. So I'll go through different steps in this talk, how imagination supervised learning can help recognition, creation, self-driving, and maybe express affection. So these are the references for the works that I'm presenting in this talk. So for future, you may refer to them. So let's start by the first step, imagination to see. And for that, I would like to introduce zero-shot learning. And maybe not all of us are aware about what brachyrochlid is, but if someone describes that to you in language and say that this is a bird that has a short orange beak and the plumage is dark above and white below, maybe recognizing this unseen bird species, if it's that for you, wouldn't be a difficult task. And this shows that we can imagine beyond what we have learned by just composing this component. Like we understand what beak is, what orange beak is, but that particular composition, that bird has an orange beak and has the dark plumage, and a plumage that's dark above and white below might be unique to this particular bird. This shows that people can learn and imagine from language description, or maybe we can build machines that learn similar to us. One thing I want to share with you, that this is explicit imagination has been successful for tasks like zero-shot learning, and this can be modeled as something like this. So you feed a language description like the one we just introduced into a GAN model that hopefully imagine how this bird may look like in some feature representation space. A successful generative model is the one that is capable of generating discriminative feature representation for different species, even if the difference is in the peak of the bird, so that you can tell them apart from one another, and not only that, can hopefully also recognize them from seen species. This has led to at that time, this is a paper from CVPR 2018 that led to a significant improvement from 37 to 42% in zero-shot learning benchmarks. And this also has been observed by several other papers that appeared in similar time in few-shot learning and zero-shot learning literature. So why should we care about zero-shot learning? Maybe that's that's another question you might think about. From like biodiversity perspective, let's say that this kid is looking at this bird and out of nowhere it flies away. And in another situation, we might actually have to fly away. Otherwise, we could be a meal to this hungry bear. In both situations, and from biodiversity perspective, we care about both the bird and the bear, and we would like to identify the instances of those species at the fine-grained level. So maybe some decision makers can take some actions. So we might imagine that we might interact with this robot that loves the environment, and this like this kid who was curious to know about this bird might ask, I saw a bird that has an orange beak, and maybe the AI system that loves Mother Nature is not clear. Maybe he will ask more and more questions till it knows already what it really means, and then it can identify that bird hopefully in a certain location, and then maybe the kid can go and look more and understand and learn more about that bird. That's one perspective for generative modeling for facilitating recognition, basically. And from let's get to the second station, imagination to create. And actually, to just clarify, the system is quite. I think I needed to comment more on this slide. The system is quite similar to standard conditional GAN model. So the input here is a description of the unseen class, and a Z vector that represents within class variation, and that will produce feature representation for that class that are then trained to trick the discriminator to believe that they are real. But at the same time, each one of the seen classes are assigned like a location, an index in a second hit of the discriminator that is assigned for seen classes. So, and this is how the model is trained, basically. Please feel free to stop me if you have any questions. That's the key. There are some other key machineries that suppresses the noise in the text description, but the spirit is the same. All right, so getting to the second stop, imagination to create. So it's also still about building generative models that hopefully facilitate creation of novel art and fashion. And in this case, let's say I'll go over creative adversarial networks. It's a paper introduced 5 years ago in the International Conference on Computational Creativity. And in this case, let's imagine that we start from a set of art style classes like Renaissance, abstract art, cubism. And the goal is, how do we encourage the model to explicitly deviate from seen art style norms? So hopefully produce something that is different, and hopefully people might like and maybe might have some emotional experiences towards it. So the inspiration came from the principle of least effort by Colin Martindale. It's a theory that relates to human creativity. And what is plotted here is, in the x-axis is novelty, and y-axis is likability or hedonic value. And what is shown here that if novelty is low, people may not like the work. But as novelty increases, people start to like the work more and more, but not for too long. When the work is too novel to understand or to relate to distinct concepts that we are aware about, such lack of understanding will lead to lack of appreciation. So let's imagine that we just feed the art data into a generative model, and see what happens. What we observe is that this might generate let's say the Mona Lisa again. It's a beautiful picture, but it's not a novel content anymore. And the point, the suggestion here, or the idea here, is that I think the GAN model doesn't have an explicit teaching signal that encourages the model to produce novel content. And creative adversarial network is about augmenting GAN model with an explicit signal that encourages it to produce something that is different from what it observes during training. So we started by these 20 art styles, including abstract art, cubism, impressionism, Renaissance, and so. And we added a loss function, and this loss function is meant to do exactly this, encouraging the content to be different. As you can see here, that this is done by an entropy loss. So the model is quite similar to GAN model, but we added another head for style classification. So let's say if we feed the painting like the Mona Lisa, we want to trick we want to classify it as real, and at the same time this will be classified to the high Renaissance style. But on the other hand, when we train the generator, we want to trick the discriminator to believe it's real, but at the same time we want the generated data, the generated image, to be different from what it have been observed during training. And we do that by encouraging the entropy over seen art styles to be high, meaning it should be hard for the discriminator to classify which art style the generated image is coming from. All right. So if we have pictures like the Mona Lisa, this will lead to a low entropy because it will be most certain which class this image belongs to, high Renaissance. If we produce an image that is more in between or more like deviating as much as we can from existing style norms, that will give high entropy, and hence the loss will be what we desire.
Right. I like it. It's really cool. So who painted it? A machine.
It's actually the first work of art made by AI to be sold at Sotheby's. Sorry, I'm late, Dana. I got caught up.
So this is one of the pieces that in 2018 was featured in at HPO Silicon Valley, but that was produced by this algorithm. And these are a diverse set of paintings that were generated by the method back then. And at that time, it got covered by New Scientist and MIT Tech Review and it was also exhibited in many places. Like next, we also implemented that in the fashion space, and we observed a similar ability for the model to produce different shapes. For example, this pants was extend arm sleeves. The model didn't observe during training like something like that, but it has observed with t-shirts and pants, and hence the model was capable somehow to produce some like fashion designs that combines both. This work is led by Othman, and joint work with Antoine, Yan, and Camille. And yeah, it was it received the best paper at ECCV in 2018. So one thing I want to share as well is that these two like tasks can circle back to help each other. How in a paper that appeared in ICCV 2019, we rethought about this wounded curve that we discussed a little earlier from human creativity perspective. We thought, how would that like be helpful to rethink zero-shot learning? And we proposed this creativity-inspired zero-shot learning work, where if we think here that in the x-axis novelty against seen classes, and y-axis is generalization performance, meaning the ability of the model to recognize unseen visual classes from the language description, and hopefully telling it apart from seen classes as well. If the model is capable only of producing for unseen classes representations in that space, like seen classes are closer to like have a smaller distance to the seen classes, right? So then the model will be confused to tell apart something like parakeet auklet from crested auklet, because they are very similar. They both have orange beak, they both have plumages that are dark above and white below, but this bird has a curved feather that comes from the top of the head of the bird. So this, if we don't have a powerful and discriminative generative model that can generate different representation given these slightly different language descriptions, it would lead to poor generalization, right? And this is not something we want. As novelty of the generations of unseen classes increases, this will expected to improve the generalization, but we don't want that to be too much to disable transfer from scene classes, because scene classes is what enable us to learn what orange beak is, what plumage means, and etc. So we just started with the same method from the CVPR18, and then we added a loss function that can be thought as an exploratory learning signal that hallucinate text representations of unseen classes. Let's call that TH. I will define in a moment what that means. But let's assume that TH is a text representation that explore the unseen space of semantic descriptions of unseen classes. And then let's feed that to the generative model. That will lead to some visual generations. We want that to trick the discriminator to believe that it's real, because we want this to be a realistic learning representation. But at the same time, if TH, with assumption that TH is a hallucinated representation of an unseen class, one thing we want to encourage that this should not be classified to any of the seen classes. And hence we added a high entropy loss function over seen classes here to encourage this exploration of the hard negative space of seen classes to be hard to classify to any of the seen classes. And hence this improved the representation when we check the results on recognizing, for example, crested auklet, an unseen class, and parquet auklet, a very similar seen class. The model was capable of like improving the performance of telling this apart from one another significantly. And we have in the paper, they reported the performance on 7 benchmark data sets, and all of them, this additional loss has improved the performance. So you can get to the paper for more details. So the search station is self-driving scenarios. So in this case, we have, let's say, in motion forecasting is a task that people in self-driving cars care a lot about. And in this case, assume that you have maybe the past trajectory of the ego vehicle and also surrounding vehicles, and you want to predict where the car is going in the future. Let's say 3 or 6 seconds. And this is a multimodal problem, because if a car is at the intersection, there are multiple possible futures. It can go to the right and can go straight, can go to the left. So by nature, this is a multimodal task. So and here in HalentNet, we proposed an approach that is also related with, that is based on generative modeling, to also improve the generalization performance of this task, with a similar idea to the one that we use for creation of art and also recognition of unseen classes. So yeah, so the baseline at that time, this is like 2021. The baseline was Trajectum++ by Stanford Autonomous Lab, and they were basically an autoencoder based method that encode the past into some representation, and then there is a discrete latent variable Z that represent the future intent, like the driving intent. So given the past and I sample Z is a 25-dimensional discrete latent variable, and every intent is hopefully predicting a possible valid trajectory in the future for the car. All right, so this is how it is designed. We complemented this by making a difference between two things, what we call a classified intent and another one called hallucinative intent. Classified intent, by classified intent, we mean that we fix during training, we fix a particular intent, we sample an intent, let's say one of these 25, and then we predict a trajectory for that sampled intent. And then we feed it we put it in the map, and then we feed that to the discriminator. And we want while training the generator, we want the discriminator to classify this to the intended like Z, like to the target intent, like that we input here, and at the same time trick the discriminator to believe that it's real. All right. So this will help the model to be more capable of telling apart predictions that comes from different discrete latent intent that we learn along the way. But let's keep in mind that these latent intents are latent classes. So this is one difference between this application and previous application. In previous applications, scene classes are known. We know their names. In creativity, we know existing scene art, scene style, art style classes. Here we learn these discrete latent classes, and here this loss is helping telling them apart. And there is another loss we call hallucinative intent loss, where what we do is that we sample an intent and then at the random time steps we predict that for 6 seconds in the future. And 6 seconds means every half a second there's a prediction. This is, let's say, 12 data points. So we pick one driving intent, and at a random time step we switch from driving intent Z1 to, let's say, Z5. Okay, but at the end that will lead to a prediction of a trajectory. We'll feed that through this system, and it will lead to a predicted trajectory. We put it in the map, we feed it into the discriminator. We encourage the discriminator to believe that this is real, and at the same time we want to make it hard to classify to any of the existing driving intents. So it's like a mix up intent. So what does this do is that while mixing up intents, it encourages the model to predict a safe or a smooth trajectory, and hence it makes the model more capable of predicting better trajectories. This reflected in the performance by let's say if we want to predict 6 seconds in the future, the final displacement error got reduced from 6.7 to 4.9. This is more than 27% reduction. And the road boundary violation, which is the percentage of trajectories that hit the road boundaries, got reduced from 19% to 9.2%. So getting to the imagination to feel stop. So this is in this work we work on. It's less related to it's related to generative modeling, but from the perspective of language generation rather than image generation. But we'll get back to that later. So in this paper, this is a joint work with Panos, Max, Gleichbeek, and Professor Gibbs from Stanford. And in this work, we focus more on introducing a data set that hopefully helps us study how do we build human compatible AI systems that are more aware about our emotional being. So most of the existing vision systems focus on recognizing maybe there's a cat, there's a dog, there's a snake, but maybe not much into, let's say, that this is something. This right now a bunch of applause, but when I observe that this is a snake, this might construct an emotional fear experience, for example, right? So there is probably less work in maybe in vision about that emotional aspect. And one goal of this district is to move one step in that direction. So the motivation is to have some more effective captions. So and embrace diversity. Some people might have positive experience from this. From getting exposed to art pieces, some others maybe not too much. In this same painting, a person felt that this dots makes him feel uncomfortable or sick. Another person captioned this felt that that this is reminds me with a night sky with the stars. Right? So if you contrast that to COCO dataset, this is an example of the COCO dataset, which is one of the most influential dataset in our community. The focus more is on factual objects that exist in the image, like for example, many large kites flying in the sky, etc. But there is less focus on the emotional aspect of the unsettling balloons. Right? So and if you go into more examples on that, contrasting how we talk about birds in Artemis dataset versus COCO captions, you will observe more differences. Like this is a picture of a bird that gives me hope. In Coco, a baby sitting on a table drinking out of a cup, and so on. So the focus is just a little bit different. And to introduce this difference, that was caused basically by how we collected the data to start with. So in this case, we have we collected data set of 455,000 on 80,000 unique paintings from the WikiArt dataset, which covers basically masterpieces and interesting pieces from our art heritage over the past like 5,000 to 10,000 years. And we ask people first, choose an emotional experience. When you get exposed to this visual stimuli, what do you feel? And you have to pick one of those or something else. Something else means that he doesn't feel anything or something different, or something different from those. And then the description here is a justification of why he or she felt that way. So after we did collect the data, we observed this distribution. Most people actually felt amusement, contentment, excitement, a small percentage of anger, disgust, fear, sadness. And as I mentioned, the goal is to embrace these diverse emotional experiences, because this is it's okay to have positive and negative expressions. So in this CVPR, we had a follow-up, like a second iteration on the data set. We named it "It's Okay to Not Be Okay: Overcoming Emotional Bias and Effective Image Captioning by Contrastive Data Collection." And in this work, we observed some opportunities in the first version, where we found there is a strong bias towards like positive emotional experiences, amusement, awe, contentment, excitement, and there is far less negative experiences. And we felt that maybe there's some bias because people know that this is art pieces. Maybe they are biased towards some emotion versus the other. And another thing that we've observed that the captions are quite generic. So some of the description we observed was something like nice looking painting with bright and nice color scheme. This is an okay description, but it's not as particular, it's too specific about this painting. And we wanted to try to do something to fix this problem. So we proposed the Artemis 2, and you can see that as a result, like this is a difference. Like before, this is a positive and negative distribution of positive and negative experiences. This is the distribution after. And the gains are basically that based on the same benchmark set, the performance with the same test training set size, there's a gain inside the score about 20%. And at the same time, we did human evaluation, and 73% of the human evaluator preferred generations from Artemis 2 model. I will explain a moment why this led to this result, like what explains this result, despite that the data set size is the same. So the thing here is that we collected the data in a contrastive way. This means that we try to encourage more and more similar images to construct different emotional experiences. So, for example, let's look at this. Yeah, I think this is not so. I'm not sure if you see this, but let's say this particular example. Like this we have here a picture of like a vase, and the feeling towards it is contentment, and this is a needle snapper painting, right? The Artemis one has this, like the blue and the deep blue purple color give these depths and makes the fruit stand out. Another, like in Artemis 2, that was the answer. The green mold on the rotten fruits on the table is disgusting. So we wanted to have by design an encouragement to have similar like paintings, like in terms of color and information, and the visual similarity are similar, but they hopefully construct different emotional experiences. The way we do that, and the reason, motivation behind that was actually, and the reason behind the name of the paper is actually related to the, It's Okay to Not Be Okay is actually a Netflix series about three friends who went through hard times, and they were helping each other to heal their emotional wounds. in some sense. So you can think of this work as an AI or data version of it's okay to not be okay. So how the data was collected is that we pick paintings, we go over the paintings that have dominant emotional experience, whether it's positive and negative, and we asked participants, given the 24 nearest neighbors, only 4 shown here, to pick an image that is similar yet construct an opposite emotional experience. So if the given one is positive, I want that person to pick one that may construct a negative emotional experiences and vice versa. So if you look, this is like a video that shows how it looks like to annotate the data with our interface. You can see that people can hover and zoom in and take a look at the painting while picking the nearest neighbor painting with the opposite emotional experiences. And based on that, they get routed to an interface that helps them annotate this with a caption that describes why they felt in that particular emotional experience. All right. So in total, we collected 260,000 contrastive examples. In terms of the benchmark setup, the dataset size of Artemis 1 and Artemis 2 are the same, but the way Artemis 2 is constructed is by the new data that we collected plus 50% selected at random from Artemis 1, and the training data for Artemis 1 is the original setup. And the evaluation is exactly the same as the original setup. So we didn't construct our own test data for fair comparisons. And you can see that this is all the 20% gains that I was referring to. And these are some example generations. We observed that the captions are are more detailed and less generic compared to the version 1. And in average, we uncovered emotional bias, and we collected Artemis 2 to overcome this bias. And this is just the example that I was referring to. And the performance was superior in terms of CIRA score and also human evaluations. 73% prefer the captions generated by Artemis 2 models versus Artemis 1 model, despite the training size is the same, and also the training model was the same. The captioning model was the same. So this is it. One more thing, and we this year at the international conference in competition creativity, we proposed something that is an improved version of CANS, like that we talked about earlier in this talk, called Creative Work Adversarial Network. So we abbreviate this as QUAN, and it's a new model that encourages encourages novel art generation. So these are some examples, and the thing that we observed is that the model is capable of produce images that are novel and hopefully higher in terms of human ratings. So these are like these two, like this slide shows the contrast between Artemis, like CAN in 2017 and QUAN in 2022. The idea of this approach is to construct a random walk class that starts from scene art style class. Let's assume that C1, C2, C3 is abstract art, cubism, impressionism, etc. And the gray points are the images, the art pieces that are generated in the current mini patch. So what we do is that we start from each one of these art style centers and then go for a probabilistic random walk for T number of steps through the gray points, and then compute the landing probability back into these style classes, into these style classes, and we're encouraging the model to deviate better from scene style classes. Technically speaking, we construct three probability matrices: one from the scene art style classes to the orange points. So this is, let's say, 3 times n, and then another one from a transition probability matrix from every generated point in the current mini patch to every other generated point in the current mini patch. That's n times n for T number of steps, and then a third transition probability matrix of n times 3, which projects this back to probability over the scene art style. So this is 3 times n times n to the power t, and then n times 3. That constructs a 3 by 3 matrix. But what does this matrix mean? This matrix means what is the probability of starting from class I and going for a random walk of T number of steps through the generated images, and then land in class J. And what we encourage as a deviation signal is to encourage this random walk to be uniform over all scene style classes. So no matter which class I start from, go for a random walk for the images that I want to be novel. I want to make it hard for the model to land in any of the classes I start from as a deviation signal. And that led to, compared to style GAN and style CAN, which is a version of CAN, but implemented on top of style GAN 1 and style GAN 2, improved significantly the ability of the model to produce paintings that have ratings of 4 and 5, which is significantly better, and it was more capable of images that are different. This is the nearest neighbor distance from the training data, and have a higher likability score. So it achieves somehow some balance and reconstructed this similar wounded curve to the one we talked about earlier. So we want to generate something novel, but not so novel to generate something that we might not be, we might not like. And in addition to that, we produced diverse emotional experiences.
Okay.
Yeah, and that led to, we did some study. This is an unconditional model, but we wanted to study whether the generated paintings would have an emotional impact on human participants, and that led to that distribution. So the model was capable of producing different images with diverse emotional experiences, but 13% of people felt that it's confusing. Like maybe this means 13% of the generated images might not be very meaningful. And these are some of the captions that people describe generated paintings. So this is, for example, the appearance resembles more an exhibition of Egypt in the museum, and etc. So going back again, like this same loss that we talked about for improving novel art generation, we applied it back for zero-shot learning. In this case, you can think of the same thing, but we generated this class centers guided by the class description of scene classes, and we hallucinate unseen classes so that it goes through this same random walk, go for T number of steps, and land into land with high entropy over these scene classes to help deviate scene classes and telling them apart from unseen classes, like unseen classes from unseen. And then that led to an improved performance in zero-shot learning as well. This is some results compared to actually, I think we compared to a generative modeling paper that is appearing at the CVPR, and the performance improved on top of the CVPR22 paper. So yeah, like this is basically the story that I would like to share with you today, and some other related work that we do is that's appearing in this conference, Visual GPT. This is a paper that tries to distill knowledge from GPT-2 model. Let me go quickly to the main idea. So the main idea is to have a gating mechanism that tries to distill knowledge from GPT, which is a language only trained model, to improve image captioning, which is producing a text description given an image. And the key idea is to produce a gating mechanism that can distill knowledge from the pre-trained language model versus what you have learned from the data. And the trick here was basically that we have the gate values that are close to 0, but not exactly 0. This allows small gradient to disrupt the existing weights of the GPT-2 model. And what we did simple change in this gating mechanism to cut it after a certain point, and this led to an improved performance, like in compared to this gating mechanism. So we have this result that shows, for example, that is a picture in low shot image capturing. This is just to clarify. This is a low shot setting. Maybe this is not the case for if you have full access to training data, this might not be valid. So a woman and girl sitting on a table with a birthday cake, and maybe other models struggle a little bit on that. This shows the performance if we train on 0.1% training data, 0.5% training data, 1% training data. And you can see in all of them, there is a significant gap. We also tried that on medical report generation data set, and you can observe that the gain compared to state of the art is also meaningful. All right, visual GPT, I would say it can connect to effective image captioning data set that we talked about earlier, because maybe you managed to collect the data in English, but there are many. We want these models to work to be more representative for different cultures and different backgrounds and different languages, but we might not have the capacity to collect data for all languages. So maybe data efficient captioning models can enable us to enable captioning system to work better in all languages with small additional data that we collect for each one of those. So this is the point I want to make, and then work a bit on the opposite direction, effective image captioning to visual art generation. Use dark color to make it seem as if ships are going to an enormous place. We have some results on that. We extended some technical novelty to enable the model to produce an INR-based representation, so that it constructs, actually, given that language description, it constructs a neural network for every image that takes XY coordinates and produces an RGB value. This enables the model to extend, to generate images of an arbitrary aspect ratio and complete and extend the scene beyond the scope that is used during training. At the same time, more to be conditioned on text. So it can extend outside the boundaries, and it also can generate images with an arbitrary aspect ratio. This is how it looks like if you applied it on standard data set like birds. So it may extend the tail of the bird, like the branch of the tree, and etc. And it was based on a paper that an unconditional INR GAN paper that we presented at CVPR last year, that basically it adapted style GAN architecture so that given a Z vector, it produces a neural network that takes as an input XY coordinate and produces RGB. And the image itself is produced by iterating at every XY coordinate and producing the actual RGB after you predict this neural network. So we recently adapted that to be conditioned on text, and we work on a bunch of other stuff for distilling knowledge for compositional recognition, like, let's say, for example, a zebra climbing, climbing over a giraffe. This might be a rare event, but you might still want to understand it. So we had some earlier work that will appear this Friday. So if you're interested, you may take a look. This is still compositional because most of these compositions are probably not seen during training. So it still relates to limited to learning with limited data. So this is really transformer, and last thing I want to conclude with is that we also propose at this CVPR tomorrow. Actually, we have our presentation style GAN V. It's I think to our knowledge the first video generated model that can train a successful long videos, an hour-long video, with sparse training points, like with only few frames, like 3 or 4 frames or something. This is led by Ivan and collaboration with Sergey from Snapchat. So you can see that this is how it looks like. It worked consistently better compared to the state of the art at the time. But as you know, like, we are in a fast-moving field. I think there are papers on archive right now that probably beats this result. And it has, since the model is inherited, so the point here is that it is only 30%, 30% better than the closest runner-up. Another thing is also only 5% more expensive than style GAN image generator. So this makes it light, and since it's based on style GAN too, it makes it easy to also do clip edits, like person with mustache, and then you provide a video, like generate a video for Barack Obama, and then we just make this clip edit, and then you can clip the video with similarly with it. So this is just perks that are inherited from style GAN too. These are some other generations with jellyfish motion. I think we have this is style time lapse. This also can extend stably for hours. Maybe some of the limitations that maybe after some point maybe some of these motions might repeat. I would say this can be a room for future work, and yeah, and these are the references and for the work that I discussed with you today. And thank you very much for being with you today.
We have it over time, but maybe we can make one question